Hello all, welcome back. Today we will be continuing our previous lecture from nozzle characteristics and nozzle flow. So myself, I am Sai Krishna from the Department of Aeronautical Engineering from the Institute of Aeronautical Engineering. So today we will be continuing with our previous topic and understanding about your nozzle flow, particularly under rockets. We will be discussing about the isentropic flow, flow properties and the characteristics of the rocket nozzle. Now coming to our thing, today we will be going through the isentropic flow through the nozzle. Now, what happens on the nozzle, what I discussed till previously is basically what happens under convergent section and what happens under divergent section, right? And what are the effects between those two temporarily. Now, kind of extending the same, what happens as per of our rocket engines, we will be considering a combination of both, that is C as well as D nozzle. So, within the CD nozzle, large fraction of thermal energy, particularly the heat energy that is being generated by the gases that are flowing from the chamber is converted into kinetic energy, because that is our main motto. Because the conversion of kinetic energy will give you the exhaust velocity of the gases, which in turn transfer to the rocket as a velocity. Now, the gas pressures as well as the temperature may drop dramatically as well as the gas velocities. Now, the expansion that takes place is a reversible isentropic flow process. Now, what happens? What do you mean by reversible isentropic flow process? We'll understand. So, when a nozzle, particularly inner walls, has a flow obstruction or a wall protrusion, right? A nozzle inner wall particularly has flow obstruction or a wall protrusion, particularly a piece of weld or a slag generated by metal melting or metal erosion, then the gas kinetic energy, right? The gas kinetic energy is locally converted back into thermal energy, recovering the stagnation temperature as well as stagnation pressure in the chamber, right? So let us understand this a bit. For example, let's say this is my nozzle, right? There is small flow obstruction. It can be a small bump, pre-placed bump, or wall protrusion, right? What happens due to this is basically whatever gases are supposed to expand against the wall, they tend to convert the energy, right? They tend to convert the kinetic energy of the gas that is being coming from the combustion chamber to a stagnation temperature as well as stagnation pressure at this particular point, right? And this would quickly lead to a local material overheating. Local material overheating, particularly in terms of melting or wall failure, right? As all nozzle inner walls must be smooth without any protrusions. And the stagnation conditions can also occur at the leading edge of the jet vane or at the tip of gas sampling tube inserted into the flow, right? Any probe, let's say we are applying in order to identify the combustion properties of that particular rocket, that also can be considered. Now, considering the same, we'll understand the concept of velocity in terms of rockets. Now, the nozzle exit velocity, let's say at y equals to 2, also called as your V2. In the previous case, what we have seen is basically hx minus hy. We have seen a derivation for hx minus hy where x and y are two separate conditions or two separate sections from which we require or we are calculating the energy transfer, particularly between two sections. Now, what if we consider x as 1 and y as 2, or can also be rewritten as 1 designate the nozzle inlet conditions and 2 designate nozzle exit conditions. Now, what happens in this? H1 minus H2, or in our case it will be V2, right? Velocity x can also be rewritten as velocity of 1, and velocity of y can also be rewritten as velocity at 2. Now, the relation that has been formulated here can be rewritten in terms of my enthalpy form difference. Now, what it suggests basically, the exit velocity, particularly nozzle exit velocity, can be rewritten in terms of enthalpy difference and the kinetic energy at first, particularly nozzle inlet. Now, this relation strictly applies where there is no heat losses, right? We are considering that there is no temperature change or negligible temperature change. Now, this particular equation, what we have discussed earlier, is within the two locations of the nozzle, within the nozzle, and within which the subscripts 1 and 2 will designate nozzle inlet as well as nozzle exit conditions. And for constant K, particularly K is nothing but Cp by Cv, and the above expression or the previous expression, this can be rewritten in terms of V2 equals to square root of 2K by K minus 1 RT in terms of pressure ratios and the initial velocity. Now, when the chamber's cross section is large compared to the nozzle throat, the chamber velocity or the nozzle entrance velocity is comparatively small. Means the term V1 square may be neglected. Now, if you are neglecting the V1 square, right? So before that, let us start. When the combustion chamber cross section is large compared to the nozzle throat, particularly if this is my combustion chamber and this is my nozzle throat, right? The area of the combustion is very large compared to the area of throat. Now, at that time, the velocity that we are considering at the beginning here can be very small, right? For that reason, what we are doing, we are neglecting. Now, compared to this, the chamber pressure, particularly T suffix 1, which is located at the nozzle inlet and under isentropic conditions, differs a little from the stagnation temperature, particularly for chemical rocket propulsion for combustion temperature T0. Now, hence, we arrive under two equivalent simplified expressions, particularly the velocity V2, which are once commonly used for analysis for rocket energy. Now, in this T1 can be rewritten in terms of T0 by M, and this ratio, as we know, coming to the next is the gas velocity exhausting from an ideal nozzle is a function of prevailing pressure ratio, that is P1 by P2, and the ratio of specific heats, particularly K, and the absolute temperature at the nozzle inlet T1, as which contains the gas constant R. Now, because the gas constant of any particular gas is inversely proportional to the molecular mass and or the exhaust velocities, particularly, and the corresponding specific impulses strongly depend on the ratio of absolute nozzle temperature, which is close to T0, divided by the average molecular mass of the exhaust gases that we are considering here. Now, the specific impulse and the exhaust velocity of an ideal rocket propulsion unit at our optimum nozzle can be seen here. Now, in this will be our equation we will look into, and this is a small equation regarding the specific impulse. A small plot has been made with respect to my ratio, that is absolute temperature to the molecular mass to the ideal exhaust velocity as well as the ideal specific impulse. Now, what happens to the ratio? As the temperature increases, the whole ratio get also increased, whereas as the temperature decreases or the molecular mass increases, as the molecular mass decreases, then also the overall ratio gets increased. Now, considering this, what happens as the ratio gets increased, right? As the ratio of the initial temperature, particularly absolute temperature, and the molecular mass M for several values of K as well as any other, what we are finding out is basically as the ratio increases, right? As the ratio increases for an individual value of K, particularly gas constant, we are getting specified impulses, right? Specific impulses of each rocket at every gas constant K as well as exhaust velocity. Now what happens in this? The grid lines that we are having are for specific pressure ratios, right? Pressure ratio with respect to inlet as well as exhaust. Now for pressure ratio of 20 or 40, what we are getting? We are getting an idealized form of specific impulse as well as idealized form of exhaust velocity. Now these can be rewritten. Let us understand this. Now a fraction, particularly T naught by M, which plays an important role in optimizing the mixture ratio, which is nothing but an oxidizer to fuel flow, the ratio of oxidizer to the fuel flow in any chemical rocket propulsion. It can be a solid or a liquid or a chemical. Now the equation that we have previously derived shows an increase in entrance gas temperature, right? And any increase in entrance gas temperature which is arising from the increase in combustion energy releases, particularly the temperature at combustion chamber, or any decrease in propellant molecular mass, particularly M, that what we have taken here, the decrease in molecular mass, particularly by using low molecular mass gas mixtures, which also can lead to rich in hydrogen, will enhance the ratio of T naught by M. Now as the ratio enhances, what happens? You will be getting an ideal exhaust velocity as well as the ideal specific impulse for that rocket engine as well as the nozzle. Now as they increase, the specific impulse is through increase in the exhaust velocity, which is nothing but V2, and thus the performance of the rocket vehicle, which influences the pressure ratio of the nozzle, that is P1 to P2, and of specific heat ratio K are less. Now from the graph, what we are understanding is the performance does increase with the increase in pressure ratio, as well as this ratio increases when the value of chamber pressure, that is particularly P1, rises when the exit pressure P2 decreases, corresponding to the high altitude designs. Now for any small influence in K, particularly, it's fruitless because of low molecular masses found in many diatomic as well as monoatomic gases correspond to the higher values of K, and the values of pressure ratio must be standardized when comparing specific impulses from one rocket propulsion system to the another, or for evaluating influence of various design parameters. Presently, a chamber pressure of 1000 psi, which is in terms of 6.894 megapascal, with an exit pressure of 1 atmospheric, particularly on ground, are used as a standard reference for such comparison, which is 68.06 as the pressure ratio. Now, for optimum expansion of nozzles, what we are considering is basically P2 equals to P3, where the effective exhaust velocity C and ideal rocket exhaust velocity V2 become equal as V2 equals to C optimal. C, which is nothing but effective exhaust at optimal state. Now, substituting C for V2 in the previous equations, what we will see, we will find out. Now for fixed nozzle, particularly exit area ratio and a constant chamber pressure, the optimum conditions occurs only at particular altitude where the ambient pressure, that is P3, equals to the nozzle pressure at P2. And all other altitudes, the effective exhaust velocity is not equals to the ideal rocket exhaust velocity. Now, the maximum theoretical exhaust is infinite, even though the pressure ratio is not, because it corresponds to the finite thermal energy contents of the fluid. In reality, such expansion cannot occur because, among the other things, the temperature of most species will eventually fall below their liquefaction or their freezing points. Thus, they cease to exist as a gas and can no longer contribute to the expansion or any other velocity increases. Now, A very high gas velocities, particularly over 1 km per second, can be obtained in rocket nozzles. The temperature drop of the combustion gases flowing through a rocket nozzle are appreciable. In an example, the temperature change from 1115 degrees centigrade in a relatively short distance. Now, let's understand regarding the nozzle flow as well as the throat conditions. Now, as of our requirement in order to create higher kinetic energy or higher exhaust velocity of the gases, we are considering supersonic nozzles. Now, the supersonic nozzles, which are also called as D-level nozzles, which are named after their inventor, whereas which also consists of a convergent section leading to a minimum area followed by a divergent section, and the minimum area which we are calling it as throat. Now, from the continuity equation, the area is inversely proportional to the ratio of V by V, and the minimum nozzle cross-section area is commonly called as the throat area, which is denoted by A suffix T, and the ratio of nozzle exit area A2 to the nozzle area, to the throat area AT is called the nozzle expansion area ratio and is denoted by a Greek letter epsilon, as we have discussed earlier. Now, the simple representation for a nozzle parameter, particularly the expansion ratio, is given by A2 by A1 or AT, where A2 is the area, nozzle exit area, and AT will be my throat area. Now, under this, the maximum gas flow per unit area occurs under this, particularly throat, where the unique gas pressure ratio exists, which is an only function of a ratio of specific heats, particularly K, and the pressure ratio is found out by setting M equals to 1. The throat pressure, that is particularly PT, from which an isotopic mass flow attains its maximum, is called critical pressure. The typical values of the above critical pressure ratio range between 0.53 to 0.57 of the nozzle inlet pressure. The flow through specified rocket nozzle with a given inlet condition, that is less than maximum, if the pressure ratio is larger, is given by Pt by P1, where Pt equals the pressure at the throat and P1 is the pressure at the inlet, is equals to the 2 by K plus 1 whole to the power of K by K minus 1, where K denotes gas constant or specific gas constant. Now, this ratio is not the value across the entire nozzle, because that is the maximum flow or the choking condition, right, which is always established internally at the throat but not on the exit plane, right. Let me just reframe this a bit. As the flow comes inside a nozzle, if I am considering this as throat, where pressure of the throat, area of the throat, right, this will be the specific point where there will be the choking condition, particularly the point through which there is no greater than amount of mass flow rate can occur. Particularly at this point, per unit cross-sectional area, that will be the maximum amount of area that it can follow. It cannot exceed that. If it exceeds, in that case, the nozzle, particularly the throat, gets damaged. So that particular phenomenon is called choking. Now, the nozzle inlet pressure particularly is very close to the chamber stagnation pressure, except in case of narrow combustion chambers, where there are appreciable pressure drop and from the injector region to the nozzle entrance region. And at a location of critical pressure, namely the throat, the Mach number is always 1, and the values that are obtained from specific volume and temperature can also be rewritten in terms of Vt as well as Tt, where T suffix denotes for throat. Now, The nozzle inlet, particularly the temperature at T1, is typically very close to the combustion chamber temperature and hence close to the nozzle flow stagnation temperature T0. Why? Because the flow directly from the combustion chamber, you are directly feeding to the nozzle, right? So as soon as the flow comes in, it gets the temperature whatever we are measuring at the end of the combustion chamber will be very similar to the temperature that is entering into the nozzle, because as we are considering for isentropic as well as the assumptions that we have taken as no heat loss. Considering these two, what we are considering, the temperature whatever we are getting is very close to the temperature that is getting at the entry of the nozzle. Now, which is also equal to the nozzle flow stagnation temperature. Now, at the throat, there can only be a small variation of these properties because it's under Mark II. And for example, let's take a gas, particularly any gas with a K value, particularly gas constant value of 1.2 and a critical pressure ratio of 0.56, which means the pressure at throat is more than half than the chamber pressure P1. The temperature drops only slightly, that is 0.91 of T1, which means it drops to about 0.9, not 0.9, 0.09, no, less than that. And a specific volume has been expanded over 60%, that is 61%. Now, the critical or throat velocity, particularly Vt, is obtained by this formula. Now, the first version of the same equation permits the critical velocity to be calculated directly from the nozzle inlet conditions, particularly the temperature at the beginning of the nozzle and a gas constant. And the second one gives Vt when the throat temperature is unknown in terms of this. Sorry, not this form, right? Now, the throat is the only nozzle section where the flow velocity is also some at local sonic velocity, particularly at A suffix t. Let me just rewrite. A suffix t equals to V dot t, because mt, particularly marked at throat, is 1, right? Now, the inlet flow from the chamber is subsonic, whereas the downstream of the nozzle throat is supersonic. The divergent portion of the nozzle provides for the further decrease in pressure as well as the increases in velocity under supersonic conditions. If the nozzle is, in any case, the nozzle is cut off at throat section, particularly, let me just draw it a bit. Now, the inlet flow from the chamber, particularly combustion chamber, is subsonic, right? Whereas at the downstream of the nozzle, right, the downstream of the nozzle, the flow will be supersonic. Right? Now, the divergent portion, particularly of the nozzle, provides further decrease in pressure, whereas in turn increasing the velocity. Right? Now, if the nozzle is cut in half, let's say for example, at the throat section, the exit gas velocity is sonic, and the flow rate per unit area will remain at such maximum, because this is the throat area. Right? It will be under Mark 1 at that particular section. Now, the sonic and supersonic flow conditions can only be attained when the critical pressure prevails at the throat as well as the pressure ratio is equal to or less than the quantity, and therefore there are basically three types of nozzles, particularly subsonic, sonic as well as supersonic. Now, A small comparison between these three is subsonic, sonic as well as supersonic. Let us understand. In the complete CD nozzle, right, throat. Now, what happens to the throat area? Right, on a subsonic flow or subsonic nozzle, the throat area is minimal, whereas, throat velocity A will be less respect to the velocity of sound, or particularly Mach 1. Now, the whatever velocity that is coming from the subsonic nozzle will be less than the velocity that is supposed to be attained at throat. Similarly, for sonic, it will be equal, because whatever velocity we are pushing through, the same velocity will be getting at the end of the sonic nozzle. Whereas for supersonic, also the throat velocity will be maximum. Whereas for exit velocity, right? Let me just rename clearly. This will be my stage 1. Let me just write it down clear, just to understand a bit. If I am considering this as my nozzle, right, and this will be my inlet, stage 1, this will be my throat, this will be my 2, right. Now, what happens under this? Let's start with the new. Now, considering for 3 separate nozzle sections, we are having the velocity, particularly the velocity at the throat, right. The velocity at the throat, what it would be? It would be less than, right, the throat velocity will be less than the velocity that you are getting under inlet of the CD nozzle. Coming to the sonic condition, the velocity will be very equal to the velocity that you are getting at throat. Now, what is the supersonic? The velocity of throat will be equal to what you are getting at the exit. Similarly, for exit velocity, the velocity is vice versa. Now, at the throat, particularly the U2 exit velocity at second exit is less than A2 if we are considering only this particular section, or let me just, if you are considering only this particular section. If you are considering sonic, right, at the time the exit velocity will be equals to the throat velocity, because the gases will be coming out with the same flow. Whereas for supersonic velocity, the exit velocity will be far greater than the throat velocity. Now, coming to your Mach number, the exit Mach, particularly at the end of the nozzle, will be always less than 1, because it's not coming till the amount of throat, so the maximum amount of flow is very well less than Mach 1. Whereas for sonic engine, because you are cutting the nozzle at exactly at throat, there will be a maximum amount of flow, so the Mach will be limited to only 1 exit Mach. Whereas for supersonic, as it's so continuously expanding, the Mach gets increased, that is more than 1. Because why more than 1 is, basically Mach 1 is already at the throat, so if it expands more than that, so it adds up the energy to increase itself to Mach more than 1. Now, coming to pressure ratio will be less than, whereas for sonic conditions it will be equal to the gas constant ratios, whereas for supersonic the pressure ratios will be larger. Now, coming to the shape, right? Now, coming to the shape, what happens during this? As soon as gas tends to compress towards the throat, you are leaving it towards the atmosphere, right? So these are the parameters that it will take care. Now, coming to your sonic condition, as the gas compresses, right, you are leaving it exactly at the throat, so that it will be leaving at speed of sound, that is equal to Mach 1. Now, coming to your supersonic, as the gas compresses, right, it tends to expand further and exit the nozzle after specified length, particularly nozzle length, right. Based on this, what we are having? We are having supersonic flow, right. Now, the supersonic nozzle is the one which is only interest for regarding rocket propulsion system, because it achieves higher degree of conversion of enthalpy, particularly the heat energy, into kinetic energy, and the ratio between inlet as well as exit pressures in all rocket propulsion systems must be designed sufficiently large to induce supersonic flow. Only when the absolute chamber pressure, right, absolute chamber pressure drops approximately below 1.78 atmospheric pressure will there be a subsonic flow in the divergent portion of the any nozzle during any sea level operation, right. And this pressure condition actually occurs for very short times during start as well as stop transients, particularly whether you are starting a rocket engine or whenever you are stopping a rocket engine. Now, the velocity of sound, which is denoted by A, is propagation of speed of elastic pressure wave within the medium, particularly sound being an infinitesimal pressure wave. If, therefore, sonic velocity is reached at any location within the steady flow system, it is impossible for a pressure disturbances to travel upstream past that location. What do you mean by that? Let's say, for example, if on any flow, let's say I am not considering any completely nozzle, at this point you are getting sonic condition, particularly Mach 1, right, on the flow. If you are considering this as my location where I am having maximum mass flow rate, particularly Mach 1, and if you are generating a shock wave, particularly a pressure disturbance, that occurs only at downstream rather than the transfer of the same in the upstream, right. That doesn't happen. So any partial obstruction, particularly a disturbance of the flow in downstream of a nozzle throat running critical mass, has no influence on the throat or any upstream of it, provided that the disturbance does not raise the downstream pressure above its critical value. Now, it is not possible to increase the sonic velocity at the throat or the flow rate in a fixed to configuration nozzle by further lowering the exit pressure or even evacuating the exhaust section. It is important that has been described as the choking of the flow, which is established at the throat or not at the nozzle or any other place. The choked mass flow rates through the critical section of the supersonic nozzle can be derived from continuity equation, where mass flow rate m dot is equals to the amount of mass that is going through particular section or at any other cross section within the nozzle for steady flow, which can be derived as AV divided by V, where V is equal to specific volume of the throat, A is the cross section area, and V will be the velocity at the throat, which defines my mass flow rate. Now, which can be rewritten in terms of this. Now, what are this? Is basically pressure ratios, pressure, initial pressure, and gas constant, and temperature, right? And the choked mass flow rate through the rocket nozzle is therefore proportional to the throat area and the chamber stagnation pressure, particularly P1. This is also inversely proportional to the square root of T by M, that is the temperature to the molecular mass ratio, as well as function of other gas properties. Now, for supersonic nozzles, the ratio between the throat and any downstream area at which the pressure Py prevails can be expressed as a function of pressure ratios and the ratio of specific heats, particularly the equation of areas, particularly AT by AY is equal to, in terms of velocity and the directional velocity, next in terms of pressure ratios and the gas constants, where Py is equal to P2, that is in terms of Py equals to P2, which is also equals to pressure at atmosphere, if you consider for within the atmosphere. And the area ratios, particularly exit area to the area of throat, is equals to A2 by A1, which is also given as epsilon, as we discussed earlier, where epsilon is my nozzle area expansion ratio. Now, the equation which shows the inverse nozzle exit area expansion ratio. Whereas for a low altitude operations, that is sea level to about 10,000 meters, particularly 10 kilometer, nozzle area ratios are typically between 3 to 30, which are depending on the chamber pressure as well as the propeller combinations and vehicle envelope constraints. And for higher altitudes, particularly 100 kilometer to higher, the ratios are typically between 40 to 200, but they have been some as high as 400 also, because at higher altitudes you will be having no pressure to a near vacuum, right? Now, similarly, for an expression for ratio at a velocity at any point of a downstream of the throat with a pressure Py, and the throat can be written as in terms of this equation, and the equation above is being dimensionless because pressure cancels as well as the velocity cancels. Now, but does not represent the Mach number, because Mach number is represented in terms of speed, particularly speed of the sound. And the last two previous equations permit the direct determination of the velocity ratio as well as or the area ratio for any given pressure ratio or vice versa, and for in ideal rocket nozzles. And a small plot has been made to understand it further, the velocity ratio to the area ratio to the pressure ratio, right? For increasing pressure ratio, right, particularly diverging section of a supersonic nozzle, for increasing pressure ratio, for a value of K, that is 4.1, in what way it changes, we'll discuss. Particularly the velocity ratio goes on increases for the value of K, for lesser value of K, right? Similarly, for the same thing, for lesser value of K, the area ratio increases as the pressure ratio increases, right? A correlation among these three terms particularly can be used to determine any one or two unknown variables with any one known variable. Particularly with the known value of K, we can determine the known value of K and the known value of pressure ratio or velocity ratio or area ratio, we can determine any one of the other, right? Now with this, for a raw condition, Py particularly is equal to P2. The equation which already pre-describes is the velocity ratio between the nozzle exit area and the throat section, right? And where the exit pressure coincides with atmospheric pressure, particularly P2 equals to P3. And these equations apply to an optimum nozzle expansion. And for rocket that operate at high altitudes, it can be shown that not much additional exhaust velocity may be gained by increasing the area ratio above 1000, right? And in addition, the design difficulties, particularly heavy inert mass, have made applications about area ratios of 350 as marginal, right? Now, continuing with the same, in the next class, we will be discussing regarding the specific impulse, characteristic velocity regarding the nozzles, and we will be continuing the topic furthermore. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.